Now we need to extend what we know about Lagrange multipliers to functions where I have three independent variables. So extending to three independent variables will give me an objective function that will have the form of w is equal to f of x, y, z. Its level surfaces are now surfaces in R3 as opposed to level curves in R2. The constraint equation will have the form g of x, y, z is equal to 0, and this is another surface S in R3. The process for finding the maximum and minimum values of f of x, y, z, where x, y, z is constrained to lie on the surface S, is very similar to working with Lagrange multipliers in two independent variables. We're still looking for points a, b, c on the constraint surface S, where the gradient of f at ABC will be parallel to the gradient of g at ABC, which is not equal to 0. So if I let f and g be differentiable on a region of R3 with the gradient of g at ABC not equal to 0 on the surface defined by g of x, y, z is equal to 0. In order to locate the maximum and minimum values of f subject to the constraint g of x, y, z is equal to 0, I have to first find the values of x, y, z, and lambda, if they exist, that will satisfy the equations. The gradient of f at x, y, z is equal to lambda times the gradient of g at x, y, z, and I need to be sure that g of x, y, z is equal to 0. Once I've identified the values of x, y, z, and lambda that satisfy these two equations, I will look at the values found in this step and select the largest and smallest corresponding values of the objective function, which then give me the maximum and minimum values of f subject to the given constraint. There are four unknowns when I'm working with Lagrange multipliers in three variables. I have x, y, z, and lambda. In order to find four unknowns, I need to be able to solve four equations. So I'm going to have to look at fx at xyz, which has to be equal to lambda times gx of xyz. Fy at xyz will be equal to lambda times gy of xyz. Fz of xyz will be equal to lambda times gz of xyz, and g of xyz has to be equal to 0. So I want to use these four equations to set up and solve an example. In my first example, I want to use Lagrange multipliers to find the maximum and minimum values when they exist of the function f of xyz is equal to x plus y plus z, subject to the constraint given by x squared plus y squared plus z squared minus 2x minus 2y is equal to 1. The gradient of f at xyz gives me the vector with components 1, 1, 1, and the gradient of g at xyz gives me a vector with components 2x minus 2, 2y minus 2, and 2z. Fx at xyz is equal to lambda times gx at xyz. This gives me 1 is equal to lambda times 2x minus 2. Fy at xyz is equal to lambda times gy at xyz, gives me 1 is equal to lambda times 2y minus 2. And fz at xyz is equal to lambda times gz of xyz is going to give me 1 is equal to 2 lambda z. Putting these three things together gives me lambda times 2x minus 2 is equal to lambda times 2y minus 2, which implies that x is equal to y. And lambda times 2y minus 2 is equal to 2 lambda z, which implies that x is equal to y is equal to z plus 1. Now I want to use my constraint function g of xyz is equal to 0. I get x squared plus y squared plus z squared minus 2x minus 2y minus 1 is equal to 0. Plugging in the fact that x is equal to y, and those are both equal to z plus 1, gives me x squared plus x minus 1 squared minus 2x minus 1 is equal to 0. This simplifies to 3x squared minus 6x is equal to 0, which tells me that x can be 0 or it can be 2. Now I need to evaluate all the critical values we get using x is equal to 0 and x is equal to 2. Those points could be at the coordinates 0, 0, 1, 0, 0, minus 1, 2, 2, 1, and 2, 2, negative 1. F of 0, 0, 1 gives me 1. F of 0, 0, negative 1 gives me negative 1. F of 2, 2, 1 gives me 5, and f of 2, 2, negative 1 gives me 3. The minimum value of negative 1 occurs at the point 0, 0, negative 1, and the maximum value of 5 occurs at the point 2, 2, 1. Let's work another example. I want to find the dimensions of a rectangular box with a volume of 16 cubic centimeters that has a minimum surface area. I have to identify the objective function. In this case, it's given by the surface area of a rectangular box. F of xyz is equal to 2 times xy plus 2 times yz plus 2 times xz. The constraint equation for the volume of a rectangular box is given by x times y times z is equal to 16. The gradient of f of xyz is a vector with components 2y plus 2z, 2x plus 2z, and 2y plus 2x. The gradient of g of xyz is a vector with components yz, xz, and xy. Fx at xyz is equal to lambda times gx of xyz. This gives me 2y plus 2z is equal to lambda yz. This implies that lambda over 2 is equal to 1 over z plus 1 over y. F of y at xyz is given by lambda times gy of xyz. I get 2x plus 2z is equal to lambda xz. This implies that lambda over 2 is equal to 1 over z plus 1 over x. Fz at xyz is equal to lambda times gz of xyz. I get 2y plus 2x is equal to lambda times xy. This implies that lambda over 2 is 1 over x plus 1 over y. This tells me that x is equal to y is equal to z. Using my constraint function g of xyz is equal to 0, I get xyz minus 16 is equal to 0. Since x is equal to y is equal to z, all side lengths can be represented by the same letter. I'll pick x and have x cubed equal to 16. This tells me that x is equal to y is equal to z, and they are each equal to 2 times the cube root of 2. This means I have a box that is a cube with side lengths of 2 times the cube root of 2. If I look at my surface area objective function, f at 2 cube root of 2 for each coordinate gives me a surface area of 24 times the cube root of 4. The question is, does this box truly minimize the surface area? Let's consider what happens if we were to let x go to infinity. If x went to infinity, the constraint equation would force either y or z or both to go to 0. This means that my surface area would approach infinity. This tells me that my point truly gives me a minimum surface area. Let's work another example. I want to find the values of L and G where both L and G are greater than or equal to 0 that maximizes the utility function u is equal to f of Lg, which is equal to 32 L to the 2/3 G to the 1/3, and subject to the constraint 4L plus 2G is equal to 12. I want to determine the value of the function at the optimal point. The gradient of f of Lg is equal to a vector with components 64/3 times L to the negative 1/3 G to the 1/3 and 32/3 times L to the 2/3 G to the negative 2/3. And the gradient of c of Lg is equal to the vector with components 2, 1. This is because my constraint equation is equivalent to 2L plus G is equal to 6. FL at Lg gives me lambda times CL of Lg, which is 64/3 L to the negative 1/3 G to the 1/3 is equal to 2 lambda. Fg at Lg is equal to lambda times Cg at Lg. I get 32/3 times L to the 2/3 times G to the negative 2/3 is equal to lambda. This tells me that L to the negative 1/3 G to the 1/3 is equal to L to the 2/3 G to the negative 2/3. This implies that L and G are equal. My constraint function C of Lg is equal to 0 gives me 4L plus 2G minus 12 is 0, where L is equal to G is equal to 2. My function has a critical value at the point 2, 2, and when I plug that in, I get 32 times 2 to the 2/3 times 2 to the 1/3, which is equal to 64. This is my optimal value of the function at the point 2, 2. So you get to try it. Pause the video and find the points on the cone described by z squared is equal to x squared plus y squared that are closest to the point with coordinates 1, 2, 0. When you're ready, restart the video to check your understanding. For this one, we want to write my objective function. My objective function, f of x, y, z, is going to be given by the quantity x minus 1 squared plus the quantity y minus 2 squared plus z squared. G of x, y, z is equal to x squared plus y squared minus z squared is equal to 0. The gradient of f at x, y, z is equal to the vector with components 2 times the quantity x minus 1, 2 times the quantity y minus 2, and 2z. The gradient of g at x, y, z is given by a vector with components 2x, 2y, and negative 2z. Fx at xyz is equal to lambda times gx at xyz. This tells me that 2 times the quantity x minus 1 is equal to 2 lambda x. Fy at xyz is equal to lambda times gy at xyz. This tells me that 2 times the quantity y minus 2 is equal to 2 lambda y. And fz at xyz is equal to lambda times gz at xyz. This tells me that 2z is equal to negative 2 lambda z. This last one implies that lambda has to equal negative 1, so that I can plug that back in and find that y is equal to 1 and x is equal to 1/2. Now, using my constraint surface, g of xyz is equal to 0, I get 1/4 plus 1 is equal to z squared. This tells me that z is equal to plus or minus the square root of 5 over 2. The points on the cone closest to the point with coordinates 1, 2, 0 are given by coordinates 1/2, 1, and plus or minus the square root of 5 over 2. Let me know if you have any questions about working with Lagrange multipliers with constraint equations in 3 variables.